I remember when I first learned about atomic orbitals, and they really confused me. I didn't understand what they physically meant or where they came from. The guy in the video just said that these balloons tell you where you might see an electron, and these are the rules to memorize these shapes. Something in the presentation had to be missing, and indeed, something was. The Schrödinger equation provides the theoretical basis for chemistry, yet most chem students learn about orbitals without actually understanding this equation. This makes chemistry feel like memorizing a bunch of ad hoc rules, when in reality, there are theoretical principles from which we can derive everything we observe in chemistry. So in today's video, we'll truly find where these balloons come from. Here's how to solve the Schrödinger equation for a hydrogen atom. First of all, what is hydrogen? Hydrogen is a bound state consisting of a proton and an electron. Doesn't this mean that we have to find the wave function for both the proton and electron? Well, the proton is much bigger than the electron, so we can consider it motionless and put it at the center of our coordinate system. The potential energy for the electron-proton system only depends on the distance between the two particles, so we should use spherical coordinates. Since our potential only sees radius, the 3D Schrödinger equation in spherical coordinates reduces to the radial equation. Solving the radial equation will give us the radial part to the wave function, and we'll attach the spherical harmonics in the end to get the full solution. By the way, this video is the fourth in the series on quantum chemistry. If you're not up to speed, make sure you check out those previous videos. This equation is messy, so let's tidy it up. Dividing by energy and defining a new variable k gives this equation. It looks even messier, so let's define these two new variables. We don't have to define new variables, but these help keep things organized. This equation doesn't have an obvious solution, so we can instead take a look at the limiting behavior of u to get some insight on its structure. As p goes to infinity, u behaves exponentially. This diverges as p gets large, unless we set b to be 0. In the opposite regime, as b goes to 0, we get this differential equation. We take the derivative of u twice, and get the same thing out, multiplied by a p term. This is something polynomials are really good at doing, so we can use the polynomial ansatz for u. Plugging in the ansatz would give this relation, and solving for r gives this. So we get this formula for u as p gets small. Now the d term diverges, so we set that to 0. Now we know how u behaves as p gets large and small, so we can try writing this ansatz, where v is some function of u. We can think of v as how u behaves when b is not too big or too small. Calculating the derivative of u in terms of p gives this, and taking the derivative again gives this. We can then plug that into the radial equation and move some terms around, which gives us this. If you've taken a differential equations class, you might recognize this as being a good candidate for power series. So let's expand v into a series of p. Doing power series stuff gives us this. Factoring out p gives us this, and then rearranging gives us this. This gives us a recipe for manufacturing new coefficients. If we know the first coefficient, c0, we can use this formula to calculate c1, c2, and so on. And we can find c0 from normalization. But we're getting ahead of ourselves. Technically, we've finished off the Schrödinger equation, but we were hoping that v of p would respect the end behaviors of u. Does it actually do that? If it doesn't, that would mean that our solution wouldn't be physical. Recall this formula for u. Since p is large for large exponents, large j corresponds to large p, and our coefficients behave like this for large j. We can then write cj in closed form like this. If you have trouble seeing how this follows, write out the first three terms of cj. This means we can write v like this for large p. And oh look, that's a Taylor series for an exponential. Putting everything together gives us formula for u of p, which diverges. That's not what we wanted. So how can we avoid this? The answer sounds a bit silly, but it's actually genius. Just don't allow large values of j. At a certain point, we have to stop counting if we want finite solutions. This isn't artificial, as long as we can find a certain set of parameters within our solution that works. Here's what I mean. If there's a special j where the series terminates, call it j prime, then this relation would have to hold for p0. But remember that p0 is also equal to this. Everything here is a determined constant except for k, and everything k is a determined constant except for e. Okay, this is where the magic happens, so stay with me. Our series will only terminate if this relation holds. But since j prime and l are integers, this only holds for when p0 is also an integer. And since p0 depends on e, that only holds if e is an integer. Let's make this more concrete. Let's define this as some integer n, where n starts at 0. Plugging things in gives us a formula for energy. Only for these eigenvalues will this series terminate. Okay, technically speaking, energy isn't an integer. What I really meant was that energy has to be equal to something which cancels out the non-integer terms of p0, and this formula does the job. We usually lump these terms into one letter, which we call the Rydberg constant. And like that, we've solved for the energy eigenvalues for hydrogen. This means that an electron bonded to a proton might only have discrete energy values. To increase the energy of the electron, you have to give it just enough energy to climb the energy ladder. Anything more or less, and the electron won't budge. This is what Balmer observed with his spectral lines in 1885. From these lines generated by emitted photons, he was able to empirically find the same formula 40 years before the discovery of the Schrödinger equation. This is, in my opinion, the greatest empirical prediction of quantum mechanics. From some wacky equation with some sus philosophical implications, we are able to naturally derive the energies of electrons and hydrogen, and that's amazing. Okay, but what about the wave function? Well, we've technically already solved that too. Using the series solution, we can generate new coefficients. The series stops when j equals n minus l minus 1, so for n equals 0, the lowest energy state, and l equals 0, the series stops at j equals 1, giving us this solution for the radial part. We then tack on the spherical harmonics to get the full 3D solution. We can find C0 by normalizing the wave function, which gives us this. But what do these solutions look like? Well, here's a hint. Moving angularly does not change the potential, which wouldn't change the wave function. So it might look like a balloon that decays as you move outwards. And indeed, it does. And that's where the balloon that confused 11-year-old me came from. Okay, that was a lot. Imagine how long it took just making this video. It's totally okay if you're confused. It took me some time to understand the solution, too. So here's some encouragement. Hydrogen is the only known element for which we can even solve the Schrödinger equation exactly. That might sound discouraging, but that implies we don't have to do the same thing for every element. We can recycle the hydrogen solution and tweak it a little bit to find energies for all the other elements. This is what's called perturbation theory, which is a topic for a future episode. But what about a Hundruel or spin or covalent bonds? What do N, L, and M really mean? We'll answer all these questions in a new series, where chemistry comes from. But for now, let's just appreciate the first real solution to the Schrödinger equation, and everything that comes after. Thanks for watching, and peace out.